Hello everyone, this is Pradyuman Gupta and today we are going to study about the B tree. We are going to study about its insertion deletion operations and we'll also look into some examples. So let's start, but let's see first the definition of the B tree. A B tree is a generalization of a binary search tree designed specially for use on disk. So B tree used to represent very large dictionaries that reside on disk. This is the special case of MB tree. B tree consists of root node, branch node, and leaf node containing indexed values in ending nodes of the tree. B-tree are a good example of data structure for external memory. It is commonly used in databases and file systems as we are studying it in DBMS. In order to maintain the predefined range, internal nodes may be joined or split. Each internal node of B-tree contains a number of keys. The key acts as a separation value which divides its subtrees. B-tree may waste some memory in the memory, may some waste some space in the memory. Since nodes are not entirely full, if the B-tree is balanced, then its search, insertion, add operation will take in log n complexity or log n steps. Now, coming to the B-tree properties, for a B-tree of order n, a B-tree cannot be empty. A B-tree should always be non-empty. The root has at least two children. Remaining internal nodes, if any, have at least C lambda by two children. All leaves are at the same depth in the tree. There cannot be different depths in the tree. Non-leaf node with k children has k minus 1 keys. It may contain large number of keys. Okay, now the next topic is insertion in the B tree. So we'll look into the steps and then we'll go to the examples. First, we'll look in the steps for insertion. Let the key to be inserted is k. Okay, so a new key is always inserted at leaf node. Like BST, we start from root and traverse down till we reach a leaf node. Once we reach a leaf node, we insert the key in that leaf node. Unlike BSTs, we have predefined range of number of keys that a node can contain. So before inserting a key to node, we make sure that the node has extra space. To insert a new node, we go down from the root to leaf. Before traversing down to a node, we check if the node is full. If the node is full, we split it to create space. Now coming to the example, here we have keys. Okay, so procedure, let's start by adding. We have 1, we added 1, we had 12, they are together. Now in step 3 we had 8, 10, 25 and 2. So 8 come to the top and 1, 2 and 12, 25 are split into 2. Now we add other, we have 17 here and 7 here, so we add them. So we got 8, 1, 2, 6 at the left, 12, 14, 17, 25, 28 at the right, and it should look like this. Now coming to the deletion. Now deletion from a BT is more complicated than insertion because we can delete from anywhere, but insertion can only be done at the leaf. Okay, so when we delete a key from internal node, we will have to rearrange the node children, otherwise it will not be balanced. Just as we have to ensure the node didn't get too big due to insertion, we must ensure that the node doesn't get too small during deletion. A simple approach of deleting might have to back up if a node other than the root along the path to where the key is to be deleted has the minimum number of keys. Then most of the keys in a B tree are in the leaves. Deletion operations are most often used to delete keys from leaves. The recursive delete procedure then acts in one downward pass through the tree without having to back up. When deleting a key in an internal node, however, the procedure makes a downward pass through the tree but may have to return to the node from which the key has deleted to replace the key with its predecessor or successor. Number of children must be according to the seal m by 2. Now coming to the deletion example, we have a tree which is have this 16, 3, 7, 13 to 20, 23 and so on. We have the row. Now in the first deletion, let's delete this 6. Here we have 4, 5, 6 in this node. So if we delete 6, we will left with 4, 5 since the 6 is gone and there's no changes to be made in the tree. Now coming to the second deletion, which will we do of 13. We have 3, 7 and 13 together. Now we will delete 13, so we have to keep the tree balanced again. So we will put 12 up again. So after deleting 13, we have this 3, 7 and 12 and 10 and 11 here. 12 move up. Now let's look into another deletion. We look into deletion of 7. As we have 3, 7, 12 together. If we delete 7, we have to merge these two. 4, 5 and 10, 11. Now as we deleted 7, we got 4, 5, 10, 11 in a single leaf, and the other tree is rest it is. Okay. So thank you and hope this presentation helps.